We're going to do a number of examples where we create a recurrence relation from a given situation, just as we did earlier when we looked at the Tower of Hanoi and counted the number of single disk moves we'd have to make to move a tower of n graduated disks from one post to another post. And we came up with this recurrence relation along with that initial condition. Well, we're going to do similar things, but while we're here, let's go ahead and solve this one. We now know how to solve this because we have the recurrence relation an is equal to 2an minus 1 plus 1. It's non-homogeneous, and that's why we waited till now to actually get a full solution for it. And so what we'll do is we'll look at the homogeneous part, homogeneous version, I'll abbreviate, and that gives us the characteristic equation. Again, I'll abbreviate for space here. Simply r is equal to 2. In the first order, it just comes out straight away and gives us r equals 2, and that's why that constant right there turns out to be the base of the power that we'll work with. Well, so we know r is that this thing right here, let me go ahead and say one more thing about it before I dive into it. So here's the non-homogeneous part, non-homogeneous. And that's just a constant. And so when it's a constant, or the very simplest kind of polynomial, in other words, then the same degree of polynomial, the constant in this case, will work as long as r is not 1, and r is not equal to 1 here. So we have r is not equal to 1. So the particular particular solution of the non-homogeneous will have the form just some constant. And if we plug that in, we get into the equation in the recurrence relation. We get c is equal to 2c plus 1, which is pretty simple to solve and gives us c is equal to minus 1. And since the homogeneous part, the part just in green above, has a solution alpha is equal to 2 to the n, where alpha is an arbitrary constant. In other words, when I say it that way, what I mean is that no matter what alpha is, that will solve that homogeneous part. Of course, we want a particular alpha that will satisfy the initial condition. But before I write that down, let me go ahead and write down the whole solution as an super h plus an super p, which is equal to then alpha times 2 to the n minus 1, the two parts we found above. And now let's check the initial condition. So since a1 is equal to 1, we'd have 1 is equal to alpha times 2 to the n minus 1, and that's just a 2 there now, 2 to the first power, like so. So 2 alpha is 2, and alpha is equal to 1. That gives us alpha is equal to 1. So we get our solution an is equal to 2 to the n minus 1. I know we played around with this in class, but I just wanted to have a record for this. So if we had the case where n is 64, that would give us a64 is equal to 2 to the 64 minus 1. So with 64 disks, not all that many it would seem, right? Just 64 disks. If it took us a second to move one disk to another post in the appropriate way, then this is the number of seconds it would take us to actually move the whole tower of disks to one of the other posts. And as we did the calculation in class, this came out somewhere in the neighborhood of 580 billion years, 584.5 billion years. So 584.5 billion years. And that's many times the length or the age of the universe according to astrophysicists. So that's one example where we went through the whole thing. The general goal of this section is to develop some ways to set up recurrence relations to count something that depends on a positive integer n when the number for a given n can easily be found if we know the number for smaller values, such as n-1 and n-2. So it's this inductive idea, really, that we've been looking at more formally in proof settings, but here we're looking at it in the case of actually developing a recurrence relation for some quantity depending on the earlier values. So let's take a case that was done on in one of the in-class exercises. Let's develop a recurrence relation together with initial conditions for the number of bit strings of length n that do not have 2 consecutive zeros. So something like 1, 0, 0, 0, 1, 0, 1 would be disallowed because it has 2 consecutive zeros. In fact, it has 3, but it has at least 2 zeros, one after another. So let's see how that works out if we look at this problem here. And what we're going to do is try to figure out how this relates to an-1, an-2, etc., whatever we need. So a nice way to do this, and this is something that we'll do many times actually, is to say, well, let's figure out if we take an, so we have n of them, let's just figure out what the starting bit is, or the starting bits. It could start with a 1 or a 0, and we'll consider those two cases separately. So if it starts with a 1, we've used 1 bit, so the remaining part, I'll say what remains here, are n-1 bits without 0, 0, and the number of ways for that to occur is an-1. That's how many bit strings there are of length n-1 that do not have consecutive zeros. So if we started with a 0 here, this is a little tricky because we can't just take the number of bit strings without 0, 0 now, because one of those might just start with a 0, 1, something like that. I'm going to erase that in a second. And that wouldn't work because doing that we'd have consecutive zeros. So the only way this works is if we have the case where it's actually 0, 1 to start it, and then we have n-2 bits without 0, 0 left to do it. And I had made a mistake up there. Let's write bits there. There are a sub n-2 ways to do that, because there's n-2 bits that are left. And so the number of ways to get a bit string of length n without consecutive zeros is an-1 plus an-2. And here we can real quickly get the initial conditions. A1, let me go ahead and highlight this first of all, just so we see what it is there. A1 would be the number of bit strings of length 1 that don't have consecutive zeros. Well, there's actually 2 of these. There's one of them. There's another one of them. Those are bit strings of length 1. There are 2 of those that do that. A2, the number of bit strings of length 2 that don't have consecutive zeros, well, I'll just list them. There's 1, 0, 0, 1, 1, 1, but I have to disallow 0, 0. There are 4 bit strings of length 2, 2 squared, but one of those is not going to be counted here, so we get 3 of them. So there it is. There's the whole setup there of the recurrence relation together with the initial conditions. We're going to do more of these in subsequent videos, but I'll go ahead and stop this one.